Now the first unit of discrete mathematics is logic and mathematical induction. For computer science students, this unit is very important. Now we have seen what is the meaning of proposition or statement in truth tables for negation, disjunction, conjunction, implication, by implication. Then we have seen how to prepare the truth table, then logical equivalence, what is the meaning of tautology, contradiction, contingency, then converse, inverse, contrapositive, etc. Now the next point is predicate, n plus predicate or n array predicate, quantification and quantifiers, logical equivalences involving quantifiers. Now, sentences with variables like x is a prime number, x greater than 3, x is y plus 7 usually occur in mathematics. These sentences are neither true nor false when the values of the variables are not specified, because whenever we are saying x is a prime number, if we don't know the value of x, we can't say whether it is true or false. Similarly, for other statements, whenever some variable is present, then we can't say whether that sentence is true or false. Now the sentence x is greater than 3 has two parts. The first part, the variable x, that is called as the subject of the sentence, and the second part is the predicate is greater than 3. It refers to a property that the subject of the sentence can have. Now we can denote the sentence x is greater than 3 by px, where p denotes the predicate is greater than 3 and x is the variable. The sentence px is also called the value of the propositional function p at x. Now if we assign the values of variables, then sentence px becomes proposition. For example, if px is x is greater than 3 and here we put x equal to 5, then 5 is greater than 3. Now definitely we can say that it has truth value true. So in that case it becomes a proposition or statement. Every proposition has truth value either true or false. Now depending upon the number of variables, we can define 1 plus predicate, 2 plus predicate, like that. A sentence containing one or more variables whose values are not specified is called a predicate or an open sentence. Now, what is 1 plus predicate? It is a predicate containing only one variable. Like a previous example that px, x is a prime number. So, it is denoted by px, which contains only one variable x. Now next is 2 plus predicate. Predicate containing two variables. It is denoted by pxy. Then n plus predicate in general or n array predicate. So it is a predicate containing n variables, say x1, x2, xn. It is denoted by p in bracket x1, x2, xn. Now these are some examples in which predicate is given. Now after assigning particular values to the variables, it becomes statement. Now in that case we have to decide what are their truth values. Let px denote the statement x greater than 5. What are the truth values of p of 3 and p of 8? Now here px is x greater than 3, x greater than 5. So p of 3 will be 3 greater than 5 by putting the value of x equal to 3. Now 3 greater than 5, that is not true. So the truth value is false. Now for p of 8, it becomes 8 greater than 5, which is true. Now in second example, px denotes x divides 77. Now we have to find truth values of p11, p of 1 and p of 3. So just for p of 11, substitute x equal to 11 in px. So p of 11 will be 11 divides 77, which is true. Hence truth value is true. Now for p of 1, it is 1 divides 77, which is also true. P of 3. So putting x equal to 3, we get 3 divides 77, which is wrong. Hence, truth value is false. Now, these two examples are for 1 plus predicate. Now, in this example, there are two variables, namely x and y. So, it is a to place predicate. Let qxy denote the statement x is cube of y. What are the truth values of q of 28, q of 82 and q27 3? Now we obtain the statement q to 8 by putting x equal to 2 and y equal to 8 in the statement x is cube of y. So the statement q to 8 is now 2 is cube of 8. But actually 2 is not cube of 8 and hence q of 8 is false. Now next is q of 8 2. So comparing it with qxy, x is 8 and y is equal to 2. So q of 8 2 is nothing but 2 is 8 is cube of 2. Now 8 is cube of 2, that is right, and hence q of 8 2 is true. Now next is q of 27 3. So again comparing with qxy, x is 27 and y is 3. Now 27 is equal to 3 cube, which is true. Now there are two types of quantifiers. One is universal quantifier and second is existential quantifier. Now see, the universal quantification of px is the statement px for all values of x in the domain. The notation for all x px, it denotes the universal quantification of px. Here this symbol is called a universal quantifier. We read for all x px as for all x px or for every x px. The statement for all x px is true if px is true for every x in the domain. The statement for all x px is false if px is false for at least one x in the domain. Now this point is very important because whenever we have to check whether for all x px is true or false, then in that case it must be true for all x in the domain, and to become false it is sufficient to show that px is false for at least one x in the domain. An element for which px is false is called a counterexample of for all x px. Now, universal quantifier for all can be expressed as for all, for every, all of, for each, given any, for arbitrary, for any. So these are different words or phrases to represent a universal quantifier for all. Now, second is existential quantification of px. It is a statement there exists a in the domain such that px. The notation denotes the existential quantification of px. Here this symbol is called the existential quantifier. Now, existential quantifier can be expressed as there exists, there is, for some, for at least one, etc. Now see, when existential quantification there exists x px is true and when it is false. The statement there exists x px is true if px is true for at least one x in the domain, and it is false if px is false for every x in the domain. So this part is very important again to find the truth value of there exists x px, that is existential quantifier. Now here are some examples to find the truth value. Let px be the statement x square greater than or equal to 0. What is the truth value of quantification for all x px where the domain consists of all real numbers? Now, domain in this case is set of all real numbers. That means for statement px, x will take the values from real number set. Now, if for every real number x, this statement holds, means statement is true, then the truth value of for all x px is true. Otherwise, it is false. Now see, if you consider any negative real number, then its square is always positive. It means it is greater than 0. For the real number 0, 0 square is 0. So it is greater than or equal to 0, that is correct. And or any positive real number x, its square is positive, so it is greater than 0. It means for every real number x, x square is greater than or equal to 0, and hence the quantification for all x px is true. Now see second example. Let px be the statement x square greater than or equal to x. What is the truth value of quantification for all x px, where first set of all real numbers is the domain of discourse and second set of integers is the domain of discourse. Now in both the cases px is same, that is x square greater than or equal to x, but we have to decide the truth value for all x px in case of real number set and in case of integers as the domain. Now again for all x px is true if it is true for every x in the domain, and is false if it is false for at least one x in the domain. Now see, in case of real number set, it contains all elements of the type say 0.1, 0.2, etc. Now, if you consider any real number x in open interval 0, 1, that means greater than 0 and less than 1, then for that real number x, x square greater than or equal to x is false. For example, if I consider x is equal to 0.5, then it is a real number. Now, what is x square? If x is 0.5, it is 0.5 into 0.5, which is 0.25, and x is 0.5. So 0.25 is not greater than or equal to 0.5. So in particular, if you consider any x from open interval 0, 1, then for all such values of x, x square greater than or equal to x is false, and hence when set of real numbers is the domain of discourse, then in that case for all x px is false. But what will happen if the set of integers is the domain of discourse? Now set of integers means the elements are 0, 1, 2, 3, 4 and so on, -1, -2, -3 and so on. So there are no members belonging to open interval 0, 1 in case of integer as a domain. So in case of domain as an integer for all x px is true because there are no such values x in open interval 0, 1 for which px is false. So even though px is same but domain is different, then in that case truth value for all x px may be different. So it depends on both px at the same time domain of discourse. Now third, let px be the statement x plus 1 greater than x. What is the truth value of quantification for all x px where set of real numbers is the universe of discourse? Now for any real number x, obviously x plus 1 is greater than x, and hence the quantification for all x px is true. Now px denote the statement x less than or equal to 4. What is the truth value of quantification? There exists xpx if domain consists of all real numbers. Now here the quantification is there exists xpx. So it is true if there exists at least one x from the domain for which this is true. So you can give just one example for which it is true. For example, for x equal to 2, 2 is less than or equal to 4. It means it is satisfied. So for infinite such real numbers, x less than or equal to 4 is true. So you can give any one example of real number x for which x is less than or equal to 4. So such a real number exists, and hence the quantification there exists x px is true. But see, for the same px, if the quantification is for all x px, then what will be our answer? Now, is it true that for all real number x, x is less than or equal to 4? No, because if I consider x is equal to 5, then 5 is not less than or equal to 4. It means for all x px is false if same px is there. Now, next, let qx denote the statement x is both even and odd number. What is the truth value of quantification? There exists xqx where the universe of discourse is the set of integers. Now, is there any integer for which there is some x which is both even and odd? No such integer exists which is both even and odd, and hence there exists x, qx is false. Now, Px is the statement x upon x square plus 1 is equal to 2 by 5. What is the truth value of quantification? There exists x px with domain of discourse, real numbers, and second set of integers. Now, by simplifying this equation, we can find the value of x for which this equation is true. Now see, x upon x square plus 1 is 2 by 5. So by cross multiplication, 5x is 2 into bracket x square plus 1. So multiplying every term in bracket by 2 and then shifting 5x on right side, we get this as quadratic equation. Now we split minus 5x as minus 4x minus x. Then taking 2x from these two terms common and negative sign from these two terms, we get finally 2x minus 1 into x minus 2 is 0. So the values of x are 1 by 2 or x equal to 2. So for these two values, this equation is true. Now the quantifier is there exists xpx. So if we are getting at least one value x from the domain for which this equation is true, then its truth value is true. Now the first domain is real number set. So actually x1 by 2 and 2 both are real numbers for which the statement is true, and hence there exists xpx is true when the domain is real number set. Now second is set of integers. Now x equal to 1 by 2 is one of the solution of given equation, but 1 by 2 is not an integer. So we can't consider 1 by 2 in this case. But another value of x satisfying equation is x equal to 2, which is an integer. Thus there exists some x equal to 2 in z for which the statement px is true, and hence the quantification there exists x px is true with domain of discourse as the set of integers. Now next is write the truth value and truth set of following predicates if universe of discourse is u equal to 1, 2, 3, 4, 5. So in this case, universe of discourse is given as a finite set. In previous examples, it was either Z or R, which are infinite sets. Now, it is there exists x such that x square minus 3x plus 2 is 0. Now, how to decide its truth value? If the quantifier is there exists. So, if there exists some element x from u satisfying this equation, then truth value is true. So, we simplify further as x square minus 3x plus 2 is 0. That is a quadratic equation. So, the factors are x minus 2 and x minus 1. So we get the values of x as 2 or 1. Now x is 1, x is 2. Both are present in u. So we can say that there exists some value x equal to 1 in u such that x square minus 3x plus 2 is 0. Hence the truth value is true. Now what is truth said? Even though the statement is false, the set of values satisfying that statement from the domain set is called as the truth set. So here the values of x are 1 and 2 which satisfy x square minus 3x plus 2 equal to 0. So truth set in this case is 1, 2. Now second is for all x, x square greater than or equal to 9. Now x square greater than or equal to 9 means x is greater than or equal to 3 because here the all values present in u are positive. Now x greater than or equal to 3 means x equal to 3, x equal to 4 and x equal to 5. These three values will satisfy x square greater than or equal to 9. It means there exists at least one x from u for which x square greater than or equal to 9 is true. Hence, for there exists x px, the truth value is true. But here the quantifier given is for all x, not there exist. So for all x means for every x belonging to u, for x square greater than or equal to 9 must be true. But see, for x equal to 1, 1 square is greater than or equal to 9. That is not true. Same way for x equal to 2, 2 square greater than or equal to 9. That is also not true. So for x equal to 1 and 2, x square greater than or equal to 9 does not hold. So for all x square greater than or equal to 9, the truth value is false. But what is the truth set? If you consider the elements from U for which x square greater than or equal to 9, the elements are 3, 4, 5. So truth set is the set containing 3, 4, 5. Now, third, for all x is a prime integer. Again, it is universal quantifier for all x. So, for every x in U, x is prime integer, then only it is true. Now, if you observe the elements of U, first element is 1 and 1 is not prime integer. So, for all x is prime integer is false. But to find the truth set, we need to find which integers are prime integers. So 2, 3, 5 are prime integers. Hence truth set is 2, 3, 5. Now, fourth is there exists x. X is the divisor of 13. Now this is there exists. Existential quantifier. So if we get at least one x from U, which is the divisor of 13, then statement is true. So the first element is x is 1 and 1 is a divisor of 13. So there exists x is divisor of 13 is true. Now what are the truth values? Out of the elements of U, only x equal to 1 is a divisor of 13. So the truth set is singleton 1.